Ready for the microphone? Good afternoon, everyone. It's my great pleasure today to introduce to you Dr. Rhonda Stroud. Dr. Stroud is the head of the Nanomaterials, Nanoscale Materials section at the Naval Research Laboratory. Dr. Stroud received her bachelor's degree in physics from Cornell University and then went on to receive a PhD in the same field at the University of Washington, St. Louis. In 1998, she moved to the Naval Research Laboratory and was a research physicist for about 10 years before becoming head of the Nanoscale Materials Division in 2007. She has a very broad range of research interests that span and almost mirror the research interests found on this campus, ranging from earth and planetary science to material science. And she is an expert in electron beam microscopy techniques. She was one of the pioneers of the use of the focused ion beam in preparing samples for transmission electron microscopy measurements, and over the past several years has built the premier electron microscopy center within the Department of Defense system at the Naval Research Laboratory. She is perhaps uniquely a fellow of both the Meteoritical Society of America and the American Physical Society of America. And I'll have you know that she is also the president-elect of the Microanalysis Society of America. So please join me in welcoming Dr. Stroud to tell us about The Universe is My Nanofab.
So thank you very much, Tim, for the lovely introduction. It's a pleasure to be back here in the Greenwald building to speak to you about research today that is ongoing at the Naval Research Lab and with collaborators both here on campus and across the country. So let me start by really explaining some of the jargon on the title and what the philosophy behind this talk and the title really are. So a lot of us in materials physics or nanoscience like to think that nanoscience is a relatively new field, something that's maybe 20 years old, or if we're generous, we'll say, oh, it really goes back a long way. It goes back to the Romans and their doping of glass with red nanoparticles to make red glass. But in fact, the planetary scientists and astronomers know what really old nanoscience is, and that's the fact that things like graphene have been around for billions, literally billions of years, produced naturally at extreme environments in stars and in the early solar system. So when I think of a nanofabrication facility, I do not restrict myself to a clean room filled with electron lithography tools. I think of stars, I think of the interstellar medium, I think of the Earth, and I think of that clean room facility. So I'm going to talk to you about how you can use scanning transmission electron microscopy to characterize nanoscale materials, whether you're making them in the clean room or you're harvesting them from the full span of the universe. So let me explain what a scanning transmission electron microscope is. I know this is an interdisciplinary audience. I don't expect you all to be experts in STEM. A STEM is a microscope that uses electrons in place of light. You use high energy electrons, so they need to be somewhere between typically 30 kilovolts down to maybe about 40 kilovolts, and this high energy gives the electrons the energy to actually make it through the sample. The majority of electrons go through material undeflected, unperturbed, don't interact at all, but some of them are scattered kinematically and may diffract in the material. They can interact with the electric field inside the material sample itself, and they can undergo inelastic scattering, which means they transfer energy to the sample itself, and the electron continues through the material, but at lower energy than the incident primary beam. So it's this choice of electrons transmitted through the sample, so starting from the source through this thin sample, about 100 nanometers, and out the other side. Choosing which of these electrons by the placement of the aperture of the detector tells you what type of image you get, tells you what type of information. So you can look for the crystal structure, the elemental composition, the bond distribution. You can look at electronic structure of materials. So it's a very versatile kind of instrument. It's not a picture-taking camera. It's something for probing the structure and composition of materials. The Naval Research Lab has 2 major STEM instruments. We actually have 4 TEMs altogether on the NRL DC campus. The first one was purchased in 2001, installed in 2004, and this is our workhorse field emission TEM. We do in situ work, so wet cell work for electrochemistry. We can look at biomaterials, we can look at nanoparticles. It really runs at scales from micrometers to about 1 nanometer or so. The newest instrument, installed in 2014, is a neon scanning transmission electron microscope. This one is upside down compared to this one, so the electron source is the bottom and the spectrometers are at the top. Both of these are about 2 Rhondas tall and weigh about a ton. The advantage of the neon instrument is really designed to get you down so you can do imaging and spectroscopy. It scales down to the single atom. All right, so where are the materials made? So our nanofab really spans the entire universe. As many of you know, as stars, as massive stars such as supernova and asymptotic giant branch stars age, they shed entire solar masses worth of dust in the form primarily of nanoparticles. And the dust from these aging stars collects in the interstellar medium, forms molecular clouds, which can then condense to form new solar systems. And as the new solar system forms, you can have a proto-sun, and you start to form a disk of dust that'll form planets. But during that process of the formation of the new solar system, most of the original signatures of the formation of the material in these progenitor stars is lost. Everything's chemically and isotopically homogenized, except for a little bit of material that hangs out at the edge of the disk, gets incorporated into the things I like to think of as failed planets and dirty snowballs, the asteroids and the comets, which preserves some of that early solar system material and the material that predates the solar system. And much of these materials are studied right here on this campus. So we have meteorites, which are chunks of asteroids, and we have interplanetary dust particles, a large majority of which are thought to originate in comets. And if you break those down even further, you can isolate the components with specific histories and specific types of stars. All right, so what do we expect to condense in the solar system? We use equilibrium thermodynamics as our guide. You have to start with a gas of some known composition. Typically, we model gas of solar composition because we know the relative abundance is fairly well of most of the elements. For a carbon-rich C to O ratio, or close to carbon more abundant than oxygen, you can form carbonaceous phases. So starting from high temperature, working your way down, you're initially likely to see titanium carbide, then silicon carbide, then you can get metal, calcium sulfide, and so on down to graphite or so. So I'm going to focus mostly on carbonaceous materials for this talk, so we're on that side of the phase diagram. All right, so taking that equilibrium condensation model as a guide, we can then go look at, well, what do we actually see when we search for these pre-solar components in our meteorites. The most abundant phases that have their origin in this prior generation of stars are silicates. The most abundant carbonaceous phases are nanodiamond and silicon carbide. Now, the nanodiamond, of course, you did not see on that prior slide with the phase diagram because nanodiamond is not a thermodynamically equilibrium phase at the types of pressures that were plotted on that portion of the phase diagram. So we have nanodiamond and the silicon carbide that we did expect. The silicon carbide is dominated by material from asymptotic giant branch stars. The nanodiamonds actually are identified on the basis of the fact that as a bulk residue, they contain signatures indicative of supernova origin. So these two materials, silicon carbide and nanodiamond, are actually important, not just to the planetary scientists and the astronomers, but also to the materials physicists and the electronics industry. Silicon carbide has, for a very long time, been industrially significant. So it's, of course, very hard and has high thermal stability. It's used for sandpaper. It's used for crucibles. It's used for telescope mirrors. It's used for armor. Electronically, it's interesting because it's a wide bandgap semiconductor that you can use at high temperature. And cosmochemically, it's a significant phase because this is commonly observed phase that condenses around carbon-rich stars. So nanodiamonds, on the other hand, are equally widely used. They're broadly scientifically important, again, for their hardness properties, so as polishing compounds and wear-resistant coatings, but also because it's carbon, it's chemically inert and biocompatible, but a highly functionalizable surface. So you can chemically modify the surface to attach other species of interest. And furthermore, you can make it both magnetically and optically active depending on which impurities and which defect structures you incorporate into the nanodiamond. So both nitrogen and silicon vacancy complexes are exploited for photoluminescence and for potential use as spintronics or quantum computing qubits, so-called. These phases are the nanodiamond phase is cosmochemically important because this was actually the first phase identified as the carrier of a nucleosynthetic anomaly that clearly indicated an origin outside the solar system. So that was identified in about 1987 by the University of Chicago group led by Roy Lewis and coworkers. And you can see here just an example of today you can actually buy these nanodiamonds from a variety of industrial sources and doped to make them look red, doped to make them look green, and so on. So how do we study these materials? It kind of depends on what your perspective, what your application, or what your basic scientific interest is. But these approaches are parallel and complementary. So if I'm wearing my materials physicist hat, I think about growing materials, controlling growth and processing so that I can optimize a microstructure and get out the most desirable properties. So I'm going to choose my nanodiamond conditions, my background gas, so I get the defect complex that I want for the photoluminescence or for the quantum computing. From a planetary science perspective, I can think about it either observationally, so I'm given the nanodiamonds from the interstellar medium or progenitor stars, and I need to determine their microstructure and composition. What are the impurities? What are the microstructural signatures that might help me figure out how they formed and what subsequent processing they experienced over their billions of years of existence in the universe. Now, if I was an experimental petrologist or taking the experimental approach to planetary science, I might actually be trying to go to the laboratory growth chambers and instead of optimizing properties for selling or making applications of the nanodiamonds, trying to control those processing conditions, exploit the kinetics and the thermodynamics to get the most similar material to the natural nanodiamonds in order to constrain those growth and processing histories in the natural environment. So what's common to each of these approaches is that really the transmission electron microscopy, which gets you the atom by atom structure, is a critical component for understanding the science of the materials. All right, so let's focus on silicon carbide. Silicon carbide is a very fun material. It has over 250 different polytypes. And each of these is formed by a different arrangement of 6 fundamental bilayers. So silicon carbide is kind of like a variable poem. Depending on how you arrange these layers, whether you go A, B, C, A, B, C, or A, B, A, B, you get a different crystal structure. In is the right side. Okay, so the industrial applications for silicon carbide include growth. So why the Naval Research Laboratory would have an active area of research in silicon carbide is the Navy needs high power electronics that can work at high temperatures with lower power loss and small dimensions. So we have a very large hot wall CVD growth system, and we focus on the 4H and 6H polytypes, and these are because they have the widest band gap. And so here's an actual NRL silicon carbide Schottky diode power module that can operate at 200 degrees Celsius at 10 times the voltage of standard silicon diodes. In the pre-solar green world, you make silicon carbide not in those CVD chambers, but in a variety of different stars. Let me just point out that pressure range here in the lab you use is something like 50 to 200 millibar, which gets you about a micron or so per hour of growth rates. In the stars, you're working at several orders of magnitude lower pressures, and you get a micron in months to years types of frames. And so the silicon carbide is actually the most well-studied of the pre-solar grain phases, and we have known grains from a variety of different types of stars, a large number that come from asymptotic giant branch stars. These are called the mainstream pre-solar silicon carbides. There are many from supernova. About 1% or so of the grains are referred to as X grains that originated in supernova, some that may or may not form from novae, and some that are thought to come from A and B stars or J stars, and possibly something the astronomers refer to as born-again asymptotic giant branch stars. So despite the very wide range, different classes of stars in which silicon carbide forms around the universe or did form billions of years ago, the crystal structures that we have found so far in the pre-solar silicon carbide, or were found up until the last couple of years, really were restricted to the two lowest temperature polymorphs. So my former office mate, Tyrone Dalton, extensively studied the pre-solar silicon carbide. He did diffraction and high-resolution TEM imaging on over 500 individual grains, which is painstaking, detailed science work I can only applaud him for. I'm not quite that patient. But in his analysis over 500 grains, he found that nearly 80% of them were the same 3C silicon carbide form. A minority were the hexagonal, and sometimes some intergrowth. But none of the 4H and the 6H that we like to grow in the laboratory for the wide band gap properties. Another way that's not quite so painstaking as the TEM work to identify the polytype of silicon carbide is through Raman spectroscopy. So if you have a nice large single crystal of silicon carbide, you can use your Raman spectrometer to get a clear signature of which polytype. The 3C, the simplest polytype, has a transverse optical mode that's triply degenerate, so you get this one nice sharp peak. These other crystal structures, so this is 15R rhombohedral, and the numbers here, this is 6H hexagonal. The number just refers to how many of those bilayers are required to form that larger crystal structure. So the TO peak for these more complicated rhombohedral and hexagonal crystal structures, it splits into 3 or more individual peaks, and thus if you have a nanoscale silicon carbide, when you're using confocal Raman to get the spectra, you get a broad asymmetric peak that's shifted in intensity away from that primary TO peak of the 3C cubic. And in fact, right here, in a collaboration between DTM and GL and the Naval Research Lab, over 184 of these grains were measured by Nan Lu, who's a postdoc in DTM, using Andrew Steele's Vitek Raman system. to determine what the polytype distribution was. And she found that, again, the vast majority, roughly 80% of them, were indeed consistent with the 3C crystal structure. You could even see the grains that were isotopically light in carbon were still consistent with 3C, but slightly shifted down in wave number. But there's a few of these grains, I think about 15 or so out of 184, which had a peak shift and shape that was inconsistent with a simple 3C cubic structure. And so I got involved at the point where we needed to determine what are those other crystal structures. Is there some other, are they 3C and there's some other explanation, or are they really these more complicated higher order structures? So here's the focused ion beam slice through one of these grains and imaged in bright field STEM. This grain, the whole grain actually had a needle shape here. This is just one portion of it. And by obtaining 3 separate electron diffraction patterns at different crystallographic orientations or zone axis, different tilt of the crystal, I could rule out both those low temperature polytypes. It's not 3C or 2H. It best fits, according to my calculations, to the 15R rhombohedral, although I can find an alternate indexing to the 8H crystal structure as well. So lo and behold, nature does make more than the low temperature polymers. When we look at the composition of this grain, so now this is a high angular annular dark field image, so the contrast here depends on atomic number. The bright stuff is the underlying gold substrate and an overlayer of platinum deposit in the fib. This medium gray is all the silicon carbide, and the bright things inside the silicon carbide are subgrains. So this large one here corresponds to the red spectrum down here, so you can see it's rich in titanium, rich in aluminum, and rich in nitrogen compared to the bulk matrix, bulk for a, this is approximately 100 nanometer area right there, so the whole grain is a few hundred nanometers across. So bulk gets us something like 2 atom percent nitrogen, 1 atom percent aluminum, but the bulk made up of stoichiometric silicon carbide. So we have definitely iron, aluminum, titanium, nitride type subgrains. This other subgrain over here is actually rich in iron. Taking a look at the next grain, so that first grain was a mainstream, originated in an asymptotic giant branch star. This one originated in a supernova. It's referred to therefore as an X grain. It has sort of 2 lobes in this cross section, and from the HADAF image you can see it does contain subgrains as well. So there's a bright subgrain, meaning higher atomic number on average than silicon carbide. There's a dark one, so that's low atomic number compared to silicon carbide. When I take the electron diffraction patterns from different zones, I obtained patterns that were nearly equally well indexed to the 6H or the 3C cubic forms. Additional zone axis may allow me to differentiate, but it's not always possible. In this case, it wasn't possible to get to an additional zone axis to distinguish. So in this case, we go back to the Raman. So here's the Raman plots of all the grains. We were looking at the 878 grain. It's this one, and here's its TO peak, and you can see that the peak is now asymmetric rather than the triply degenerate 3C type. So this is more consistent with 6H than 3H, and actually in the last year, a group out of Germany, so a combination of Münster and Mainz researchers indicated they also had 6H grains that they thought formed in a or they knew from the isotopes formed in a supernova. All right, so the compositional maps of this grain show major elements are silicon and carbon. There's also iron rich. So there's the iron subgrade. It's got a little bit of nickel. You can probably just barely make out. There are also titanium, and there's aluminum, nitride-rich grains. Interestingly, there's magnesium that's distributed all across the grain that spatially correlates with the aluminum. That's because that magnesium is actually the decay product of the aluminum-26. So that's actually purely magnesium-26, magnesium mapped with the EDS spectrometer. The nitrogen also mostly spatially correlates with the aluminum, so it seems to be primarily in solid solution with the silicon carbide matrix. All right, so what does this mean for the condensation environments, the stars in which these grains are produced? Well, we've learned from this study that not all grains have the lowest temperature polymorphs. It's not all 3C2H and the intergrowth of those two particular phases. And this isn't entirely surprising. The free energy differences between the polytypes of silicon carbide are actually really small, and in a laboratory experiment with the same pressure and temperature, you get coexistence, co-formation of all four of these polymorphs. And it's affected by epitaxy of one grain on the other, the nucleation of one grain and growth on the existing surface, and the incorporation of impurities such as aluminum and nitrogen. We also see from these pre-solar grains that subgrains are really common. So we saw the iron nickel rich grain and the aluminum nitride grain, and these provide an additional constraint of the thermodynamic conditions. And we need to go back to the phase diagram and look not just at the carbides, but nitrides as well for constraining the environment. So let's talk about diamond now. So as I mentioned earlier, the pre-solar nanodiamonds are a really important phase in cosmochemistry because this is the first phase found in meteorites with the isotopic signature indicative of the extrasolar origin. And there's a paper in Nature in 1987 by Lewis et al. Showed that the krypton and xenon isotopes in these residues measured in bulk shows these nucleosynthetic anomalies that are indicative of a supernovan origin. But in fact, there's only one xenon atom for every 10 to the 5th nanodiamonds or so in the bulk isotope measurements of carbon and nitrogen. So nitrogen makes up roughly 3 weight % or so of these nanodiamond residues. Those isotopic compositions are in fact completely consistent with the majority of the nanodiamonds have been formed inside the solar system. So the question a lot of cosmochemists or meteorologists have wondered for 40 years or so now is where do these really forming? Is it inside the solar system, in the interstellar medium, around just supernova stars? Is there an asymptotic giant branch component? And there is no way yet to get the isotope composition of an individual 2 nanometer particle. So there are people trying with the atom probe to get carbon isotope signatures nanodiamond by nanodiamond, and they've had some reasonable success, but it's still fairly dicey, and you certainly could not measure these isotopes in the individual nanodiamonds. So we can look at the nanodiamonds using transmission electron microscopy. In fact, the first discovery paper in '87 used electron diffraction. So this is a powder electron diffraction pattern, meaning you're doing an average of all these individual nanodiamonds, not just one pattern per nanodiamond. And this is kind of state-of-the-art or maybe more routine-ish analysis in the late 80s by electron microscopy. Later, Tyrone Dalton again came along and used the Arizona State high voltage, high resolution TEM to look at these nanodiamonds and compare them with nanodiamond produced by CVD and by detonation. And he argued, based on the distribution of the twins in each of these structures, that the majority of these meteoritic diamonds were probably formed by chemical vapor deposition in stellar atmospheres. Today's scanning transmission electron microscopes actually let you go in and look not at the atomic plane resolution, but down to the single atom resolution. So this is image I obtained at Oak Ridge National Lab before getting my own aberration-corrected stem, in which you can resolve single atoms and single layers of carbon. So this is a single sheet region of the image where you can resolve the ring structure of the disordered carbon. These areas where you see the parallel lattice planes, these are the crystalline nanodiamonds. This one is about 4 nanometers across. These are about 2 nanometers across. And the individual white dots here are single atom impurities. We can not just measure the crystal structure, but we can confirm where we have diamond and where we have disordered carbon. We can look at the bond structure of the sheet carbon and distinguish based on the electron energy loss spectra. So this is the carbon K-edge spectra. We can see where we've got pure diamond. So this is the fingerprint signature of sp3 carbon at the interior of this 2 nanometer. So the scale bar is 2 nanometers. The diamond itself is 2 nanometers. Out at the edge, it's mostly sp2 carbon. You see that in a lot of detonation diamonds as they form a graphitic-like shell, but in this case there's actually sp2 carbon that extends way beyond the edges of the diamond, and in some places the diamond appears to be fully terminated as a fully sp3 product, which means probably there has to be hydrogen there. I don't think you can terminate with straight carbon bonding and maintain sp3. All right, so here's what that looks like if you're sitting in front of the electron microscope. These are, again, this is a nanodiamond. The stuff that looks sort of spidery in between is all the sheet carbon, and the little white spots moving around are real atoms individually diffusing across the surface of the nanodiamonds. So this is the particular movie is a 10 image frame series. Each image takes about 100 milliseconds or so. So you can actually do the dynamics of diffusion in different low-dimensional materials using one of these microscopes. This is at room temperature with the 60 kilovolt electron beam, so there's some energy to promote the diffusion transferred from the electron beam itself. All right, so if we wanted to know what those individual impurity atoms are, because those are going to help us distinguish the origins of the individual atoms, we could use the quantitative image contrast. So HADAF, high energy annular dark field images, are in fact quantitatively dependent on average atomic number. So we can take a line profile off the edge into the vacuum into single sheet region carbon and see that 0.045 in intensity corresponds to a single sheet of carbon, and then go measure an individual impurity atom and discover this one's 0.45, 10 orders of magnitude, an order of magnitude higher, and that's going to translate to an atom of this, so chromium plus or minus Z of 1 or so. Now, that's actually a really slow way to do it. You may want to get the average or bulk composition of the nanodiamond residue, and by bulk, in this case, I mean an area of 9 nanometers by 12 nanometers. And we can see that these residues contain a lot of different impurities. So I already told you the nitrogen there is at 1 to 3 atom percent. There's oxygen, which can be enhanced by the treatment of the residue to isolate this from the meteorite. Fluorine is, again, a product of the dissolution from the meteorite. Sodium, aluminum, silicon, phosphorus, sulfur, and chlorine may or may not be associated with the host meteorite, so it's extremely difficult to get the chemistry clean enough that you've washed away every impurity atom that came out of the meteorite. But we do think some of these species could be attached at least to the surface and possibly, in some cases, implanted into the interior of the nanodiamond. We can go down from that bulk, 9 nanometer by 10 nanometer. So here you see the evidence that I work on a PC and not a Mac. So we've got the automatic scrolling. But anyways, we can make a measurement off of 2 nanometer nanodiamond. So there's my sampling box right there, and see that we have carbon counts, carbon to nitrogen ratio different from bulk. So the nitrogen appears to be primarily associated with the nanodiamond. When you make the same measurement off the edge of the nanodiamond, so on the disordered sheet carbon region, you see greater oxygen to carbon abundance than you do on the nanodiamond. So the oxygen is primarily affecting the sp2 carbon and probably comes in from the dissolution. All right. So we can go one step further. We can actually measure impurity by impurity. So we can put the raster box down around a single impurity atom and count X-rays off of that atom and on the underlying carbon and see that it's silicon. So in 9 seconds with an 80 picometer beam, I can tell you what an individual atom is. And this was the world record for X-ray detection of single atoms in electron microscope. It's probably going to be broken tomorrow, but because the electron microscopy field doesn't stand still. But we have one of the world's best instruments for getting energy dispersive X-ray spectra off of atomic scale materials. All right, so why should you care about that single silicon atom? Because if you want to go hunting for the nanodiamonds in an astrophysical environment, you might want to look for an absorption or luminescence signature from the silicon atoms. The nanodiamonds intrinsically are not active in the IR, but you can get a luminescence signature from a silicon vacancy impurity if it's incorporated into the nanodiamonds. And a group out of Russia, Sharayev, and co-workers proposed that the silicon vacancy luminescence feature they were seeing in the nanodiamond residues was intrinsic and could be used as a way to go out and make astronomical observations of nanodiamonds in space. But what the STEM data that we took shows is, in fact, the silicon atoms are diffusing rapidly over the surface of the materials and probably are mostly simply products of the acid dissolution or so on. So I think this vacancy feature could be equally well attributed to the fact that they've got a coating of sp2 carbon over the nanodiamond. This is annealed, and although this feature is well associated with incorporation of silicon C vacancy complex into the interior of the nanodiamond, this boundary between graphite and nanodiamond and silicon is not that well understood at this point, and I think this is an equally likely observation. In fact, I've been working with a group out of the University of Washington, Peter Pazowski and his graduate students and coworkers, looking at diamond anvil cell laser heated produced nanodiamond samples. So Peter and his graduate student, Matt Crane, who I believe is going to be out here working with Faye in a couple weeks, have been making nanodiamonds by starting with carbon aerogels, loading them in their diamond anvil cell with argon that infiltrates the pore structure of the nanodiamond. So as they increase the pressure and increase the temperature using the laser, they can preserve the porosity intrinsic to the aerogel, but get the high pressure structure of diamond. I've been able to help them confirm that they have, in fact, nanodiamonds. Their early studies showed that they had adventitious nitrogen and silicon, giving them luminescence. They worked hard on changing their chemistry for the aerogel synthesis, moving away from the base catalyst synthesis, because you can leach silicon out of the glassware when you use basic chemistry to do your preparation of the sample. So they started to work with acid catalyst generated aerogels. They still, according to the HADAF, have silicon atoms incorporated. So the bright white spots here, again, are silicon atoms sitting on the nanodiamond surface, and we can confirm that with the electron energy loss spectra. The only thing in the spectra are silicon and carbon, But in this case, the photoluminescence is missing the signature that would occur out here of the silicon vacancy complex. So in this case, the silicon atoms are sitting on the surface of the aerogel and stay on the surface even through the conversion to nanodiamond. They rapidly diffuse across under the beam the same way the meteoritic nanodiamonds showed silicon diffusing rapidly across. But they're not incorporated, otherwise we would see them in the photoluminescence signature. And so this paper is under review at the moment. So the last thing I wanted to talk about are there limits to this parallel approach or the intersection of what forms in space and what you form in the laboratory? Are we really, if we search long enough and far enough in the universe, to find everything that can be made? And I think the answer is no. There really are limits, constraints by abundance and thermodynamics that prevent some materials from forming naturally in space, even over billions of years. And one of those is illustrated by the so-called meteoritic quasi-crystals. So I first became well acquainted with this material actually in a seminar given here by Paul Steinhardt, and I was so excited for this to be reality because my PhD thesis is on metallic quasi-crystals, not the aluminum systems, but the titanium systems. And my current research involves a very heavy component that's meteoritic. So I thought this was really just made for me. But it's too good to be true. And so although the oxygen isotope measurements show that these phases out here, which are spinel and other components associated with calcium aluminum rich inclusions, have an oxygen isotope signature indicative of formation in the early solar system. So the meteoritic looking component of oxides really is meteoritic. The quasi-crystal metal itself really doesn't belong there thermodynamically, and you can go back to the phase diagram and see why not. So here, if we're condensing in an oxygen-rich atmosphere, the aluminum is going to come out either as corundum or hibonite as you keep cooling. It's going to come in oxidized form. The iron will not be mixed with the aluminum. It's going to be in metallic iron. And the copper is just too low in abundance to have formed this major phase of aluminum copper iron. So the thermodynamics says, wow, this is a really unlikely scenario to find major aluminum oxide-rich phases coexisting with metallic aluminum that's also alloyed with a cosmochemically much less abundant material, copper, which has very different redox preferences or conditions. So thermodynamics is probably not. The way to distinguish is to go in there and look for signatures of a cosmochemical origin of that aluminum copper-rich phase. You know, I'd have to say that there are data that indicate those signatures are not there. They have not yet published, say, magnesium-26 measurements, as we saw in the supernova or originated silicon carbides and so on. So, you know, it breaks my heart a little bit to say it, but this quasi-crystal is not from space. It's most likely synthesized in the laboratory, and the two phases met each other somewhere in a diamond anvil cell in a terrestrial laboratory. So just to wrap up, the physics and chemistry of materials are really the same, whether you're studying them as made here in the laboratory or as made for you somewhere in the universe. Nanomaterials are not new or not as old as the Romans. They're as old as the stars themselves. And this includes things like nanodiamond and graphene, some of our most actively researched materials. It doesn't include quasi-crystals. And the key underlying capability or knowledge you need to really develop and understand these materials and their history in the solar system is atomic scale imaging and spectroscopy. Thank you.
Questions?
I'm just curious, when you do those high resolution, can you do, you're talking about this surface versus interior. Can you do a 3D imaging of those?
Yeah, so you can do electron tomography where you tilt the sample view from different directions and reconstruct. There are some limits because the atoms will rearrange a little bit under the electron beam. So, you know, depending on how beam sensitive material, you may or may not be able to capture enough images before the system has deformed. But yes, atom by atom electron tomography is one of the holy grails right now people are working on.
So there's a lot of processes between a star and sample, you know, like sputtering in the interstellar medium, hydrothermal processes on meteorites and so forth. I mean, are you able to piece apart the different
Yes, I mean, that'd be whole different multiple talks, but those are exactly issues we've looked at. So another postdoc who was here, Aki Takagawa, who worked jointly with the DTM with Larry and Connell and me down at NRL, we had pre-solar aluminum oxide grains which showed clear signatures of impacts at high enough energy. They probably happened in the interstellar medium. So we could see what we think is shock processing in the interstellar medium in those particular grains. Aqueous alteration on the asteroids shows up as affecting the shape and composition of the organic matter and also silicate minerals, and you can see the signatures of those in detail in the electron microscope. The problem is, you know, different phases record the alteration with different reliability, and you're overprinting multiple process. So, you know, we're not going to run out of questions anytime soon. And, you know, getting a definitive single answer is takes some thought and cleverness. But obviously, there's a lot of work going, a lot of expertise to address those questions here. George?
So thanks for a great talk. That movie, the movie was beautiful, showing the atoms moving around. I was just wondering, I think two things. I gather which are the brighter atoms that we saw were silicon were moving. Is that correct?
So yeah, let's just go back and see. I think. So I'm not. Let's play it. Right. Okay. So the image intensity of each of those individual spots is indicative of its atomic number. So a large fraction of the ones here moving are silicon, but not all of them. I think there's also sulfur. I've seen some phosphorus. I've seen tiny nanoparticles of palladium. So there's refractory metal nuggets that are more or less affected by the acid dissolution that can get dispersed in here. So a lot of different species. But silicon's the dominant one, and I think it's because they're laboratory contamination sources, glassware, and also it's a major mineral in the host meteorite, so it's hard to get rid of all of it.
Okay, so my question was somewhat twofold, and it's a twofold question that's enveloped in my own ignorance. But one, I'm interested in why are they moving, and two, what is the valence state of these silicon atoms, and can you assess that?
Yes, if we can track one long enough with EELS spectroscopy, we can understand the silicon oxidation state. Yes. So I think they're diffusing rapidly across the surface for two reasons. Well, one, it's the surface and not through the nanodiamond. Two, it's a 60 kilovolt beam and some energy. There's some elastic scattering. In fact, I can coax them to move with the electron beam. They like to follow the electron beam around. And that's a whole different interesting area of can you engineer single atom impurities periodically in materials by beam steering. And people have started to look at this in bulk silicon and other impurities. A 200 kV beam, you can steer an antimony around and so on. I think that these are simply fizzy-sorbed impurity silicon for the most part on the surface. It's room temperature, so we like to think of the atoms, I don't know, at least I do, and naively think, things are mostly fixed in place at room temperature and you have to heat them up for stuff to move around. That's not true on the surface. I mean, real surface scientists will tell you there's all kinds of crud moving around all the time at room temperature. Yeah. We just don't usually get to peek at it. Yeah.
Okay, so my question is more technical. I would be interested to know from your experience, is there any possibility, for example, to look this electronic microscopy and say Raman scattering exactly from the same grain, or even better from the same molecule, or for example, a small nano tube or something like that? What would be your experience?
So there is an aberration-corrected stem at NIST that has a Raman system installed in it. So it's not a confocal, well, it is a confocal system. They port a laser beam through an objective aperture port to irradiate the sample while you're looking at it with the electron beam. The spot size of the laser, is a few hundred nanometers. So in order to interrogate, they want to do single carbon nanotubes. They have to spatially separate the nanotubes from each other. So they have to cast a dispersion where you only have one nanotube per few hundred nanometers. The signal turns out to be not that great. The Raman collection efficiency in this geometry is pretty poor. And although it sounds in principle interesting, they in fact have better success with cathodoluminescence integrated into the electron microscopes.
Hi, so you spent some time talking about your observation of silicon carbide polytypes. Do you observe any evidence for any diamond or proposed diamond polytypes, such as Indiamond or Lonsdaleite, in your samples?
Yeah, so I have not seen Lonsdaleite, and in the meteoritic nanodiamonds, I haven't seen any other sp3 bonded diamond type at different crystal structure forms. It's an active area of research to try and mate together different layers of graphene and chemically modify them to force them to be locally sp3 bonded. And I'm just not going to comment on other phases that might come into that.
Next question. So while I'm walking the microphone over, Alex had a technical question. What are the prospects for long working distance lenses to focus electron beams and things maybe like a diamond cell at high pressure?
I wouldn't give up your Raman systems anytime soon. Yeah. So, I mean, you're not going to get through the diamond. So at a 60 kilovolt electron beam, I like my samples to be 20 nanometers or thinner. So, to the highest energy electron microscopes ever made tend to be a mega electron volt, so a million volt. Right. Yeah, you destroy the materials before you actually get anything useful. Yeah.
Okay. So those are very nice images. My question is, besides impurities, if you have like a vacancy, can you look at that as well, or is it not possible?
It depends. Yeah, in principle, yes. So you may or may not be able to image a vacancy directly. It used to be totally impossible, and now it is possible depending on the geometry of the sample. So if you have perfectly flat faces, so there's no other height variation, so they're not dimples or helix in the sample, then the image intensity contrast can be directly interpreted. So where you see a dark spot, there has to be a vacancy. That turns out in practice to be very hard to achieve, and that would mean you were also working with a very thin sample of only one element. there are spectroscopic signatures. So the EEL spectroscopy is your most adaptable or applicable way to look for point defects. And people, so there's a paper out of Arizona State where they claim to have measured carbon vacancies, and I think hydrogen in the nanodiamonds. I'm not sure whether I believe their data yet or not. It's very, so it's a very small pre-edge feature that can be easily explained by variations in the background. It's a really hard problem, yeah.
Maybe short question
Sure.
joining that. So nitrogen vacancy in diamond, is
Mhm.
that possible to visualize as well, like a pair?
So you cannot see an individual, you can see an individual nitrogen atom substituted into a single sheet of graphene. By the time you add the second layer of carbon and make bilayer graphene, you no longer have enough contrast to tell whether there's a nitrogen substituted somewhere in one of those planes. So you will not directly see an individual nitrogen atom inside a nanodiamond, but potentially you can see the EEL spectrum signature of the presence of that nitrogen, both by directly detecting the nitrogen K-edge absorption and by its modification to the carbon K-edge structure. The signal to noise is tough. You can, under the electron beam, move some vacancies around, you know, so this is what the Arizona State group was trying very hard to do. They were not doing it with the STEM, so they weren't spatially resolving it. They were doing it with TEM mode, so parallel illumination and collecting the spectrum from the whole nanodiamond at once. They have some reasonable variations to their EEL signatures. You know, I think it needs to be reproduced with STEM and on multiple samples that are well understood. Yeah.
Any more questions? So I think it's phenomenal, all the advances that we've seen in these electron microscopy techniques, and now it seems that it's routine that we can do single atom imaging and single atom spectroscopy like you showed, and we can measure precise electronic structure of clusters of atoms. I wonder if you might indulge us with your speculation as to what is the next big thing in electron microscopy.
Just one, so right now, there's not a huge continued effort in trying to make the beam spot sizes smaller. So we can get, you know, an 80 picometer resolution probe with the current generation of instruments. Where there's a lot of work is on better detectors for improving the signal to noise, to lower the amount of radiation exposure